Hello everyone. So today we are gonna learn how to calculate the propagation delay and the effect of capacitance on the delay. So let's start with the propagation delay first. So this is our waveform of input and output. So what is propagation delay? So basically propagation delay is nothing but a time taken by the circuit to execute the input waveform and give the output waveform. So it's basically the time consumed by your circuit. Okay, so it's a difference between input and output. So to measure this, we take the half of the value of input and output. So when my input reaches to 2.5, that is exactly half of 5 volt. So when my input reaches to the 2.5 volt, I start my trigger and I measure it till my output reaches 2.5 volt. So now we have a clear cut idea of what we are gonna do. So let's start with it. I'll just copy the statement and we are measuring propagation delay trig. Okay, now this is the thing. So we are measuring input to output. So our input is start from so our trig is gonna start with input. So my trig statement will have input node. Okay, so just be careful with this, and I want it to start measuring when it reaches to 2.5 and it is in upward direction, that is it's rising. TD0, then target. We are targeting V output. It's already there, V output. Then value, I want it to be 2.5 and my output is falling down. So I'm gonna write here fall. Okay, so be careful with this statement over here. It might be a little confusing. So I just want you all guys to be very thorough with this concept. So where we have to use the rise and where we have to use the fall and the value and the node. So be thorough with this and we'll just simulate it now. Okay, if you have any problem in understanding the statement, then where we have to use which node and rise and fall, just comment it below or write me an email, I'll be there. So this is our propagation delay, it's around 2 nanoseconds. That's great. Okay, so now basically we just have to change the capacitor and we are gonna see how our output, how our delay is affected with the capacitors. So I'll increase my capacitance to 5. I'll just add 2 more zeros. Okay. If you all guys could imagine the output I want you to. So we are increasing the capacitance and that's how our output looks like. Very ugly, right? It's not acting like an inverter anymore. Just because we increase the capacitance, it's not functioning properly. The reason is our capacitance is now increased, so it's taking a lot of time to uh, fall down and again to rise up. If you all guys know, there is a formula of delay, that is a delay is directly proportional to resistance and capacitance of the transistor. So we call it as RC delay. So this is the effect of that delay. So just because our capacitance is increased, our delay is gonna increase, right? So we have to keep this value 250 only. Okay. What will happen if you reduce this value? Time will reduce, right? The delay would be reduced. So if you want the faster circuit, you have to reduce the capacitance. But here is a twist. This is the output capacitance, right? So it is connected at the output. I hope you all guys know why we connect output capacitance. What's the significance of that capacitance? That capacitance actually represent the input capacitance of the next stage. Okay, very confusing statement, I know. When we have a big circuit, uh, we have many circuits connected to each other. So now let's assume that this is a we have designed this inverter. Now let's assume that we have one more inverter at the output of this inverter. So we have two stage inverter now. So this output is connected to the input of the PMOS and NMOS of the next stage transistor. So and you all guys know that each and every device has input capacitance. Why we have that? Because we put a oxide in between gate and the channel, so that just because of that oxide over there, we get a input capacitance. We call it COX, oxide capacitance. So it is that capacitance which we have represented over here as 250. So in order to decrease this output capacitance, the next stage, the input capacitance of the next stage should be smaller, and in order to do that, so in order to reduce the capacitance, you have to increase the oxide thickness. And when you increase the oxide thickness, you are actually increasing the delay of that transistor, because when you increase the COX, you are when you decrease the COX, your current is actually decreasing. Your IDS is directly proportional to your COX. So if you decrease the COX, your I is gonna decrease, and if you have less current flowing through your circuit, of course it will take more time for the output capacitance of the next stage inverter to rise to VDD. So there is a trade-off here. You can't increase the capacitance, you can't decrease the capacitance. It has to be somewhere in between. So VLSI is actually full of trade-off. So you have to balance it. And I think that's it for today. In the next tutorial, we'll design the layout for the inverter schematic. Okay, bye bye.